Greetings, judges. We are Calvin Chen, Liheng, and Shivang Bhargava, undergraduate students from NYU Tandon. Our coach is Dr. Lindsey van Wagenen, also from NYU Tandon. Our team number is 1130, and we are answering problem B. Thank you for taking the time to watch our video, so without further ado, let's begin our presentation.
This viral video from 2018 shows Sammy, the Major Mitchell cockatoo from the Karakin Black Cockatoo Conservation Center, spinning on a bike wheel.
The prompt states, can you replicate and model this phenomenon? Assume that you have a bicycle wheel mounted vertically and a small device is mounted on the wheel. The device can move a small mass attached to the wheel, and hence the wheel. Is it possible to find a way to move the mass so that the wheel and the mass can rotate? Is it possible to do this if the mass only moves in the tangential direction, or can you also do so with a radial component as well? Our interpretation of the prompt hits four main questions. 1. Can we create a model of a bird like Sammy? 2. Can we have Sammy 2.0 start from rest from top of the wheel and still rotate? 3. Can we direct Sammy 2.0's controlled movement so that he makes full revolutions around the wheel? And 4. If in addition to tilting, we have Sammy 2.0 crouch and rise while spinning around the wheel, will this increase the speed? Our assumptions about the scenario are the following. We assume Sammy has the height of an average Major Mitchell cockatoo, but that his weight is on the heavier side as he doesn't have to compete for food in the conservatory. Also, images allow us to assume that Sammy is bottom heavy. We assume when Sammy crouches, his center of mass moves in a line that goes straight through his feet. We also assume when Sammy decides how much to tilt and in what direction, he uses his pivot point's overall angle on the wheel as the tilting parameter. We assume Sammy can only tilt a maximum of 1/8 pi. Also, we assume that the only external force acting on our wheelbird system is gravity. Finally, our last assumption is that there is no friction of any kind in this system. These are the main components of Sammy 2.0 and his wheel, the system that replicates the motion of Sammy on his wheel. As we assume there is no friction acting while the wheel rotates, we have our wheel rotate on a frictionless bearing. We use a 700C bicycle wheel, since for decades it has been the most common road wheel type. In addition, there are thin rods placed axially along the outer rim of the wheel just like in the video, making the rim heavier than a typical 700C bike rim. We use a small mass to represent Sammy's center of mass, being pivoted by a regular servo motor. This point mass is attached to the servo motor with a massless rod that can act as a servo pneumatic cylinder, capable of precisely changing the distance from the servo to the point mass. These are the three stages of our modeling process. In stage 1, we use angular dynamics to create a differential model for Sammy's motion. In stage 2, we directed Sammy's tilting in a differentiable manner, maximizing the amount of time the torque was high. Finally, in stage 3, we simulated Sammy crouching, decreasing the distance from the pivot point to his center of mass when the torque was low, and increasing it when the torque was high. These are our variables that we defined. We have three angular variables, theta, psi, and phi. Theta pertains to the total angle that the pivot point has traveled. In the image shown, theta is 0, so theta is not displayed. Psi is the tilt angle with respect to the radius traveling through the pivot, and phi is the angle that is made by the extended radii through the pivot point and the point mass. In the image shown, the phi and psi are greatly exaggerated to clearly show what they represent. In actuality, our model has an initial psi as only 1/10,000th of a radian, to show that even with an almost vertical start, a full revolution is still possible with Sammy's motion. G is the acceleration due to gravity. R is the radius of a 700C wheel, which is 311 millimeters. Since his center of mass is fairly low in his body, we can say that L max, or the maximum length of the pivot to the point mass, is 7 centimeters. Our last three variables all pertain to the mass of objects. Sammy 2.0's mass is 0.43 kilograms, which, as stated earlier, is on the heavier side from Major Mitchell's. M is the total mass of the system. Finally, the mass of a single spoke is 6 grams. In stage 1, we used the rotational version of Newton's second law, where net torque equals force times the lever arm, which also equals moment of inertia times angular acceleration. We used trigonometry and definitions of concepts such as center of mass and moment of inertia to create expressions for these variables. Plugging in all these variables and solving for alpha gives us the model at the bottom of the screen.
In stage 2, we control Sammy 2.0's tilting in an only psi variable, and psi uses theta as its parameter. The control equation is differentiable, which is important for our differential model. It also helps optimize the amount of torque applied to the system, which is crucial as we are trying to increase the energy of the system with SAMY 2.0's movements. Our model is impossible to solve by hand, so we use MATLAB to numerically solve this differential equation. MATLAB gave us a plot of total theta versus time. We can see from the graph that since the initial tilt angle was small, it takes a while for SAMY 2.0 to start moving. Every revolution, SAMY 2.0 rapidly spins through the bottom half of the wheel, while it moves slower through the top half, which is to be expected as the gravitational potential energy gets transformed into kinetic energy, which then gets stored as potential energy. In the 25 seconds, SAMY 2.0 completes 3 revolutions around the wheel. This animation is a visual representation of our data from MATLAB. As we can see, our interpretation of the graph was correct, as the bird takes a while to start moving, but then quickly spins through the bottom before slowing down towards the top. In stage 3, we refine our model by simulating Sammy crouching, thereby adding radial motion. This decision was influenced by the conservation of angular momentum, which states if the moment of inertia is smaller than it was before, the angular velocity increases. We say that Sammy can move his center of mass a maximum of 4 centimeters by crouching down. In the wheel image below, the arrows signify the motion of the wheel. In the length versus theta graph, as you can see, our control of the length corresponds to the resistance the motion of the bird has to gravity. When the bird is at the right or left of the wheel, or when the bird is affected by gravity the most, the length from the pivot to the point mass is either at its greatest or its smallest, and length is in the middle at the top and bottom of the wheel, where gravity affects motion the least. As expected, the Stage 3 model looks very similar to the Stage 2 model, but unlike the first model, in which there were barely 3 full revolutions, Sammy has traveled almost 4 revolutions in the 25 seconds, signifying a greater speed. As you can see, unlike the previous model, Sammy 2.0 still has quite a bit of speed when he reaches the top of the wheel. These two theta versus time graphs are for a comparison with the first and second models in the long term. While both graphs have increasing angular velocities, shown by the nonlinear curve, the superior speed throughout Stage 3's model is shown by the nearly double total theta on the right side graph. The barely noticeable jaggedness in the beginnings of both graphs is representative of a larger period of oscillation in early Ts, which is soon replaced by smooth curves, further proving the increasing angular velocity as time progresses.
The motion of the object does have to change as the angular velocity changes, but our equation describing psi and length will stay the same, as it uses theta as its parameter. But since theta is its parameter, if the angular velocity is changing, then that means that the theta is changing at either a faster or slower rate, so then the motion of the object will have to change accordingly. In addition, the maximum speed of any oscillation will occur at the bottom of the wheel. However, since there is no friction, Sammy 2.0's motion keeps adding energy to the system, so theoretically, there should be no maximum because the speed keeps increasing as time goes on.
This model is somewhat sensitive to variable changes. This was to be expected though, as different weighted and heighted birds will react differently to the wheel. There are two main places for improvement in our model. The first is when the initial theta isn't zero, especially when it starts really low on the wheel. The bird's movements should be able to add enough energy into the system to eventually make full rotations around the wheel, essentially becoming a child pumping himself on a swing. However, our model was focused on reducing energy loss, so when starting at the bottom of the wheel, SAMY 2.0 resists the counterclockwise motion when trying to pump up the wheel. Also, this model assumed an ideal world with no friction. The possible improvement would be to determine what type of dampening term we could add to the model to emulate dissipating energy due to friction.